Welcome to the debate. Usually when we think about software execution, we imagine a sequence of events.
Right, like a recipe.
Exactly. It's very much like reading a recipe in a kitchen. The computer starts at step 1, it moves to step 2, it evaluates a condition.
Like checking if we have enough flour.
Yeah, exactly. And based on that, it branches off to the next appropriate step. It is inherently iterative, it's, associative, and for half a century, we've sort of just accepted the friction of reading that recipe line by line as a fundamental, unbreakable law of computing.
Right, and our entire industry's solution to that friction has really just been, trying to read the recipe faster. We build better parsers, we design more aggressive just-in-time compilers, we add more cache.
Yep.
But at the end of the day, we are still fundamentally turning pages in a book, reading step-by-step instructions.
Exactly. But what if you didn't have to read the recipe at all? What if instead of a sequence of instructions, your entire program was compressed into a single, perfectly static, multi-dimensional geometric object?
Which sounds like science fiction.
It does, but you don't read it. A processor just observes its physical boundaries. That is the radical premise we are examining today, drawn directly from the formal ledger and system architecture of a technology called Gnosis.
Right.
Gnosis is a graph-first programming language and toolchain where every program is a topology. It's a directed graph where the edges between nodes don't carry data in the traditional sense.
They carry geometric semantics.
Yes, semantics like fork, race, fold, vent, process, and sliver.
It is an entirely different paradigm. I mean, it literally replaces the concept of control flow, the whole if this, then that logic with structural geometry. You aren't evaluating conditions anymore, you are traversing a shape.
And our central question today is, does Gnosis's purely geometric theorem-bound approach to computation, where throughput is dictated by mathematical proofs rather than benchmarks, represent the definitive optimal future of software execution?
Or, conversely, do its inherent epistemological limitations and its reliance on what the system calls the void boundary reveal a rigid framework with, frankly, critical blind spots?
That really is the core tension we need to unpack.
It is.
So, to state my position plainly, I believe Gnosis's mechanized proofs and non-associative geometric routing successfully bridge the seemingly impossible gap between abstract mathematical perfection and, quite honestly, unprecedented runtime performance.
And I take the opposing view. While the sheer speed is undeniable, the pursuit of provable optimality is a localized illusion, and the system's own formal admissions of undecidability expose profound practical limits to treating all software as universal geometry.
I have to admit, when I first read the documentation on this, my head spun a bit.
It is incredibly dense.
Oh, absolutely. But when I look closely at the Gnosis architecture, I see the fundamental resolution of the execution bottleneck. We have spent decades trying to optimize that associative control flow. Gnosis just replaces that entirely with structural geometry.
Right.
I point directly to the system's core mathematical foundation, something they call THM server optimality. This isn't a benchmark where they just ran the code a million times to see how fast it went. It is a composition of 14 mechanized theorems.
Verified using TLA Plus and Lean 4.
Yes, mathematical proof checkers. And crucially, it has 0 sorry placeholders in the proofs.
Yeah, and for those unfamiliar, a sorry in Lean 4 is basically a mathematician saying, trust me, this step works, I just haven't written out the proof yet.
Right, a gap in the logic.
Exactly. So having 0 sorries means the computer has rigorously verified every single logical step.
There are no gaps. It mathematically guarantees critical path makespan and exact, non-asymptotic speedups. But it goes beyond abstract rigor into actual physical optimization. Take the amplituhedron serialization.
This is the fascinating part.
Right? If you're listening to this and wondering what on earth that is, think of a traditional software program, a complex, iterative, abstract syntax tree with maybe 100,000 branches of logic.
A massive tree.
Gnosis takes that sprawling tree and collapses it into a static 28-byte Grassmannian tensor, a file format called .not.
It's quite the compression algorithm.
It's staggering. I mean, think of a Grassmannian tensor like taking a massive, sprawling 3D pop-up book and flattening it down into a single, highly dense barcode. You don't read the pages anymore. A scanner just looks at the shape of the barcode.
Which is a 49,604 times size reduction, if I recall.
Exactly. But more importantly, it achieves O of 1 load times. You bypass parsing completely. The geometry engine just reads 4 boundary scalars and computes the execution volume instantly.
Instantly.
To my mind, this mathematically renders traditional associative execution totally obsolete.
Well, I hear the enthusiasm, and the math is undeniably elegant. But my perspective is that Gnosis is severely constrained by its own absolutism.
How so?
Well, it builds a beautiful, mathematically perfect cathedral, but it's fundamentally closed off from the messy reality of practical computing. Gnosis claims to be driven by theorems, right? So let's look at its own theorems.
Okay.
The system includes a mechanized proof, literally named optimality_undecidable.lean. The math itself explicitly records that global optimality is provably undecidable.
Which they openly acknowledge in the ledger.
Yes, they do, but acknowledging a ceiling doesn't remove the ceiling. The system achieves its performance by relying on what it calls the void boundary.
Right.
Let's unpack how that actually works. The void boundary is basically a maze where the computer only remembers the dead ends. It's a rejection history.
Right, it maps the failures.
Exactly. It tells the system everything it has tried and mathematically ruled out, but it fundamentally cannot tell the system what it has never tried. So you are replacing adaptable, traditional, conditional logic with these rigid, highly specific geometric shapes.
I see.
It is mathematically elegant, yes, but it is a highly specialized abstraction. You are sacrificing practical adaptability for a localized, highly constrained perfection.
I see why you think that, but let me give you a different perspective on how this geometry plays out in practice, because it's not just theoretical.
Sure.
Let's look at the topological raycaster benchmark in the Gnosis documentation. Normally, if a program needs to search through data, say finding a specific user in a database of 500,000 cells, it uses linear memory string parsing. It reads through the data sequentially.
Right.
Gnosis replaces that with affine projection.
Right, casting a ray through the volume.
Precisely. Instead of reading strings, the system treats the data like a 3D object and shoots a mathematical ray through it to find the intersection point.
Yeah.
And the results are staggering. They ran this against a highly optimized V8 engine baseline. The V8 just-in-time compiler loop took 120 milliseconds to scan the cells.
And Gnosis.
The not-graph Schubert slicing took 1.43 milliseconds. That is an 84 times speedup. If zero conditional logic is evaluated and geometry alone dictates the execution boundary, haven't we eliminated the primary source of runtime latency? We aren't checking conditions, we are just casting a ray through a shape.
Well, I come at it from a different way. I am not disputing the 1.43 milliseconds. It's incredibly fast.
It is?
But we have to look at how the octonionic compiler actually achieves that routing. It routes physically by breaking mathematical associativity. It maps all topological operations to the imaginary bases of the Fano plane.
Help me understand why that's an issue. The Fano plane mapping is exactly what allows the engine to route so quickly.
It is, but think about what it requires. This system relies entirely on mapping logic into 54-dimensional float 64 blocks. And that happens in the not-graph app zone, which, to be fair, works brilliantly for purely algorithmic calculations.
Right.
If you have tightly constrained tensor math, where you can predictably map an operation to a 54-dimensional volume, it's perfect. Think of it like a set of fixed mathematical train tracks. But real-world computing is rarely a pure terminal algorithm.
You mean the business logic side of things?
Exactly. Real-world software requires the flexibility of traditional associative logic because human business rules are messy, they're iterative, and they're highly conditional.
Yeah.
When you abandon associative control flow, you force every unpredictable user interaction into a rigid geometric cast. It's like trying to use a perfectly calibrated particle accelerator to chop vegetables.
Ha ha, okay.
It's the wrong kind of precision. The real world doesn't neatly map to the imaginary bases of the Fano plane.
I'm not convinced by that line of reasoning because the documentation explicitly shows this geometric logic scaling seamlessly into highly unpredictable environments.
Really?
Yes. Specifically network transport. This isn't just trapped in a local tensor calculation. Look at the prismatic refraction wire protocol.
Ah, the vomit bits protocol.
That is their exact phrasing in the architecture docs. Vomit bits as fast as possible and let geometry figure out the shape.
Yeah.
Think about how standard web traffic works. Data is wrapped up in an envelope. HTTP headers, framing, explicit lane assignments, so the receiving server knows exactly what to do with it. Prismatic refraction throws out the envelope entirely.
Right.
They are emitting raw bytes over the wire with absolutely no framing and no shape commitment.
Which sounds like absolute chaos. How does the receiving end know what it's looking at if there are no labels?
That's the brilliance of it. Instead of reading an envelope, the wire layer performed deterministic, content-addressed lane assignment mid-flight. It uses content-addressed hashing.
Okay.
The data itself acts like a unique puzzle piece that only fits into one specific geometric hole on the receiving end. And if you think that only works for perfectly clean math, look at the scrambled DNA reassembly test.
Right, the cancer genes test.
They took 20 real cancer genes, massive, messy datasets like KRAS and TP53, and completely scrambled the input byte order.
They fragmented it across multiple lanes.
Across 16 lanes. And using just content-addressed 48-bit FNV1A hashes, the wire recovered the exact shape from the content alone.
Wow.
The geometry perfectly reassembled the DNA. Every single block count matched. Every DuckDB row matched. Scrambling the input didn't change the settled lane structure.
So it solved the puzzle.
Exactly. As they say, data delegated to geometry. If it can perfectly route and reassemble fragmented genetic code across a chaotic network, why wouldn't it handle standard application state?
I'm sorry, but I just don't buy that. Let me tell you why.
Okay.
The DNA test is a brilliant parlor trick, but we have to look at the underlying nature of the data. DNA sequences, FOSTA files, are static, high-entropy, permutation invariant datasets.
Right.
Permutation invariant protocols excel when the entirety of the content dictates its own shape, because the sequence inherently knows what it is. But think about standard web traffic. Think about a micromutation in a distributed database.
Like a single user updating a profile picture or changing a small permission toggle in an app.
Precisely. In standard HTTP framing, that tiny mutation is wrapped in a lightweight, predictable header. The routing layers can instantly read the envelope and say, this is a permission update for user X, and route it without breaking a sweat.
Sure.
But in prismatic refraction, enforcing tenant-isolated, content-addressed lane assignment mid-flight for a steady stream of unpredictable low-latency micromutations introduces a massive computational overhead.
Because the system has to constantly figure out the geometry of every tiny change?
Yes. You are forcing the network to constantly compute FNV hashes and resolve 54-dimensional geometric collisions just to know where a tiny state change belongs. It is vastly overcomplicating the problem. Standard framing handles that gracefully because it doesn't try to be mathematically profound. It just reads the envelope.
But the overhead isn't massive. The wire efficiency benchmarks clearly show Aeon flow framing operates at a 0.03% overhead, compared to something like Nginx's HTTP 1.1, which sits at 0.89%. The geometry actually reduces the tax at the edge.
It reduces the byte size overhead, yes, but look at what it costs in computational effort. It fundamentally shifts the burden from reading a simple string to epistemological guessing.
Guessing?
Yeah, if it has to constantly compute these collisions on the fly, it reveals that the system isn't actually executing perfectly. It's just guessing very quickly. Which brings me to the fundamental theoretical ceiling of this entire system, which is the kernel gap.
This is where the debate gets truly fascinating. The kernel gap is the measured distance between the system's provable mathematical perfection and its actual runtime performance.
Exactly. Gnosis claims to be the first server whose throughput is a mathematical theorem. But how does it actually compile these topologies?
Through racing.
Right. It uses in-process compiler racing. You have different compilers with names like Betty,
Frankie, Beckett, and Eon Logic. 6 compilers race against each other on every input, and the best one wins.
And they use the sliver plus 1 strategy to guarantee the most efficient path survives. To use your earlier metaphor, it's like sending 6 different mice into that maze of dead ends simultaneously to see which one finds the center the fastest.
Right. But look at the variability of those mice. On the Frankie.gg topology, the Aeon logic compiler has a 0 microsecond kernel gap. It hits the provable optimal floor. It's mathematically perfect.
Yeah.
But the Betty compiler, which is their deepest, 13-phase verification compiler, has a 275 microsecond gap on that exact same topology.
That's a compelling argument, but have you considered what that variability actually proves?
That different compilers have different strengths?
It proves the system is essentially guessing. They rely on 11,016 void boundary rejections across their forest passes. They are building a training signal entirely out of failures.
Yes, this proves local optimality. But because they rely on this epistemic void boundary, learning only from what didn't work, it mathematically guarantees that true global optimality is unreachable. You only know what you've ruled out. You are forever confined to a local maximum.
That's an interesting point, though. I would frame it differently. You are looking at the existence of the kernel gap as a flaw. I look at the formal definition of the kernel gap, which is backed by 8 theorems with 0 sorry, as the ultimate triumph of the system.
Wait, how is failing to reach global optimality a triumph?
Because the gap is measurable, it is finite, and it is shrinking. Think about a traditional execution environment. Take Bun, or Node, or even native Rust. What is the measurable distance between your code's execution time and true mathematical optimality?
Well, it's unknown. You just benchmark against a baseline and hope it's fast enough.
Exactly. It is entirely unknown. You're just guessing in the dark, hoping your JIT compiler does a good job today. Gnosis has mapped the dark.
Right, but
Yes, global optimality is provably undecidable. Gödel and Turing taught us a century ago that absolute limits exist in mathematics. But Gnosis provides a formal surface where the distance to perfection is a known, quantifiable metric.
I see that, but
And let's look at what that local maximum actually yields in practice. In their May 2026 direct materialization rerun, the native Rust cold start on a 20th order Fibonacci sequence was an astonishing 4.68 milliseconds.
it's fast.
A node environment takes around 86 milliseconds just to wake up. Even highly optimized Bun takes 25 milliseconds. Gnosis isn't just finding a local maximum, it has found a local maximum so elevated that it renders traditional runtimes fundamentally obsolete.
But you have to look at what you trade away to get there. Yes, you get a 4.68 millisecond cold start. But to achieve that, you have to write your logic in a system where operations must map strictly to semantic edges like fold and vent.
Right.
You have to ensure your data cleanly fits into a flattened Grassmannian tensor. You have to submit to a shared God formula universe kernel that literally fails closed. It completely shuts down if your topology isn't mathematically admitted.
The universe admission is automatic for executable paths. It's just a safeguard. It ensures you don't run broken math in a live environment.
It enforces absolute determinism. And determinism is a beautiful thing in a theorem prover or in aerospace engineering. But in global software development, we need systems that degrade gracefully.
You think so?
Absolutely. We need systems that can interpret ambiguous inputs, that can handle a malformed JSON payload without the entire geometric volume collapsing just because it failed an intersection test on the Fano plane. Achieving millions of requests per second on IO-Ring is a phenomenal engineering achievement.
It is.
But to me, Gnosis feels like a Formula One car. It is the absolute peak of engineering, but you can't drive it to the grocery store. It is too specialized for everyday use.
I'm not convinced by that line of reasoning because the Gnosis tooling explicitly accounts for the real world. They haven't abandoned the developer experience.
How so?
They have a transparent JIT compilation pipeline modeled right after TypeScript. When a developer runs a pure .gg file, the system automatically checks for a compiled .glonot artifact.
Right, caching it.
Exactly. If it exists, it bypasses AST parsing completely. It provides an uncompromised developer experience while securing production-grade parsing speeds right out of the box. They aren't asking developers to manually write in 54-dimensional float arrays. They are providing a toolchain that seamlessly lowers human-readable, messy code down into geometric perfection.
But the perfection is still bounded by that void boundary. The system's observer is fundamentally compiled differently from the observed. The meta-iteration relies entirely on rejection.
Right.
It's a closed loop that assumes all possible optimal states can be reached just by bouncing off the walls of failure. I just don't believe that holds true for the infinite variability, the sheer chaos of human-driven software execution. You can't mathematically prove human unpredictability.
Well, let's summarize where we've landed on this, because it really highlights the core philosophical divide.
Absolutely.
My position remains that Gnosis represents an objective leap in how we process and transport information. By abandoning the outdated crutch of associative control flow and string-based memory parsing, it replaces the guesswork of traditional execution with theorem-backed topological geometry.
Right.
From the constant O of 1 load times of the amplituhedron tensor flattening that pop-up book into a barcode, to the exact mathematically proven speedups of the server architecture, it achieves a level of performance that is no longer just measured by benchmarks, but guaranteed by formal logic.
And my position is that while the mechanized proofs and the sheer operational speed are undeniable, Gnosis's heavy reliance on the epistemic void boundary reveals its limits. Because global optimality is provably undecidable, the system is fundamentally a highly specialized local maxima.
Yeah.
Its geometric determinism and its reliance on content-addressed mid-flight lane assignments make it a brilliant solution for static algorithms and specific high-entropy data like DNA processing. But it is simply too rigid, too demanding of mathematical perfection, to serve as the universal future of adaptable, everyday software execution.
Despite our philosophical divide on the universality of the system, I think we both find ourselves highly aligned on several of the foundational shifts Gnosis brings to the table, specifically the move away from string-based serialization.
Absolutely. I think any engineer looking at this has to applaud that. The introduction of the GeoNot binary native format is a profound advancement.
Huge.
Moving away from the computational overhead of JSON stringification and base64 wrapping to achieve an immediate 25% reduction in wire size during tensor traversal, that is a massive practical win. Every single network hop benefits from that efficiency, regardless of whether you buy into the broader geometric philosophy.
And I think we also agree that the integration of formal mechanized proofs into everyday deployment is a massive step forward for the industry as a whole.
Yes.
Taking tools like TLA Plus and Lean4 out of the purely academic realm where they were previously reserved for designing microchips or verifying spacecraft logic and making them gatekeepers for actual running server topologies elevates the standard for what we consider production-ready code.
I wholeheartedly agree. Even if I question the geometric constraints required to get there, bringing formal, zero-sorry mathematical verification to the runtime level is a standard I would love to see adopted more broadly across all software paradigms.
There is still so much more to explore in the Gnosis material. We barely even touched on the system's ability to expose ambient law directly into the execution path.
Right, treating physics as code.
Exactly. The system handles quantum literals natively. It incorporates direct physical constants like the speed of light and Planck's constant as first-class values without dimensions. It raises fascinating questions about how closely our software code can or should mirror physical reality.
It really does push the boundary of what computation fundamentally is.
It leaves us with a lingering question, circling back to how we started. Are we ready to stop treating software like a tangled ball of yarn that we have to carefully unravel step by step, reading line after line?
Right.
If we can compress our logic into a perfect static crystal, observing its edges instantly rather than reading its contents, we might just eliminate the friction of execution entirely. But we have to decide if we are willing to let the rigid laws of mathematics dictate the boundaries of what we can build. Thank you for joining us on The Debate.